Hello guys, Assalamualaikum warahmatullahi wabarakatuh and a very good evening I wish to all of you. So today I'm going to present differentiation method, which is Dunn method. So it's used, you can actually differentiate between capacitive contribution and also diffusion contribution of your supercapacitor or even supercapacitor. So my name is Muhammad Nur Hafiz bin Mustafa. Here is the presentation. So a little bit about introduction. Dunn method normally is used to differentiate capacitive current, or some might call it diffusion limiting or diffusion control current. So you can differentiate between these two. Okay, then we are using cyclic voltammetry. Make sure the CV possesses the redox peak. If no redox peaks, you might consider Transative method instead of the Dunn method. So this is two formula that important in this step. The first one is current at certain potential or at fixed potential equal to K1V. V is the scan rate plus K2V power half, scan rate power half. So then we want to make it into linear equation. We might want to convert this formula into y equal to mx plus c. So we divide our equation with scan rate power half. So we got I divided by scan rate power half equals to k1v power half plus k2. So this is can mimics the linear. The linear equation can be translated into y equals to mx plus c, where the k value is constant and I is the current, v is the scan rate. So when you plot this graph, you can get exactly what we want. You can get the value of k1 from the gradient and the value of k2 from y-intercept. Then when you substitute the value into the equation, you can get the capacitive current and also diffusion control current. Okay, let's look at the procedure one by one. Step 1, run and collect cyclic voltammetry at various scan rate. So it's preferable for you to run at low scan rate, for example 1 to 10 millivolt per second. In this case, I run from 1 to 6 millivolt per second. So make sure your peak have redox peaks. If no redox peaks, better proceed with Transative method rather than the Dunn method. Okay, next, fix a potential. Step 2, fix a potential and read the current from different cyclic voltammetry. For example, I fix at 0.35 volt. So I read here the potential using the origin software. What is the current value at different scan rate, different CV graph. Okay, next, step 3, plot I versus scan rate power half versus scan rate power half. So you can get a plot like this one. For example, I have run from 1 to 6, but I only include 5 data because one of data is very far away. So this is what you get when you are measuring the current and you divide by half of scan rate, you get the response and you plot with the half of the scan rate. So using the origin, step 4, determine the K1 value, the slope, and also the K2, which is the y-intercept. Did you remember the equation? So current divided by scan rate power half equal to K1V half plus K2. K1V 1 over 2 plus K2. K1 is you can get from the slope, K2 value from the y-intercept. So from origin guideline, this is for the origin guideline, you can actually go to analysis, fitting and fit linear. So you can get the red line here and they will calculate the value of the slope and y-intercept for you. So basically you already get the value of K1 and also K2 by using the origin software. Okay, this is step 5 to calculate the contribution rate. So you want to calculate the contribution rate. What is the percentage? Just include the value of K1 and K2 because the scan rate, you know, for example, the scan rate is 1. So let's go back to the other slide. When the scan rate is 1, so you get the value of K, for example, just now is 0.9 times 1. So you got around times 100, you got around how many percent? Like for example, 90%. So that's one. When you substitute, you can get the capacitive value and diffusion value. To get the contribution rate, the capacitive divide by capacitive plus diffusion. The same things to get the diffusion rate. Diffusion divided by capacitive time plus with diffusion. This is simple mathematics. Then you can plot the contribution rate versus the scan rate. Okay, next is procedure number 6. So procedure number 6, when you want to proceed to plot the graph, so what you need to do first? First, you need to differentiate current at a certain scan rate. Meaning here, you want, for example, this is our CV. We want to plot diffusion or we want to plot capacitive. So always remember, the one that close to the middle is capacitive. The graph belongs to the capacitive, while the one at the out layer is diffusion. So always remember, so it's become easy later. We have our 4 more steps, step 7, step 8 and step 9, how to plot the graph, so stay tuned. Okay, this is the procedure 6. Choose one scan rate and measure the oxidation and reduction current response at certain potential. So here you can, for example, here I'm using 1 millivolt per second. So I measure the current response at each designated potential window. Here at 0.0, then 0.05, 0.1, 0.15, 0.2, 0.25 until 0.5. So basically here we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 times 2, 22 points, where you need to measure the current response at oxidation and also the current response at reduction. So obviously, the more the point, the more accurate. If you want to do every 0.001, it's okay. Depend on you. Normally people are using 20 points, is okay. You can go up to 100 points to get the value of each potential. So this is what the table looks like. You can see that I have a potential. I set the potential with the increment of 0.05. You can do increment of 0.01. It's up to you. And measure the reduction and also the oxidation current is very important. You can measure that using the origin. And you already calculate the percentage of diffusion and percentage of capacitive. So you can just use the formula to get the reduction current after you get the percentage. For example, here R after is after 0.15%. What happened to the value of current? So this is reduction potential, reduction current response. This is oxidation current response after the percentage contribution. So it is important to get this table first before you can plot. And last but not least, procedure 7, you can use the contribution rate percentage and determine the new current response at its potential. So at this step, you get step 7 is from the other table. So when you plot using origin, you can have the green color graph, which is you can determine the capacitive, which is 59.1%. This is for one scan rate. If you want to do for the other scan rate, it's no problem, but it's quite tedious. Normally people just plot the other scan rate using the bar chart. So this one, normally we just shows only one scan rate to mimic what happened in terms of the contribution rate. So if you didn't like to do the capacitive like this one, you can also do both capacitive contribution and the other one is diffusion contribution. It doesn't matter, but you need to do twice this time. Okay, next is the procedure. Aside from producing contribution rate graph, we want to measure the B value. Step 8 is determine the B value. At fixed potential, for example 0.35, find the current response at each scan rate and plot log current versus log scan rate. The same step as step 1, you fix a potential. Somebody might curious and asking, I don't know what kind of potential, just choose which one you see different in current response. In here, I'm choosing 0.35 because we can see obvious current response. Okay, make sure at fixed potential, you can't say here 0.35, scan rate 2, you go to 0.4, cannot, always at fixed potential. So you got the value of current, you are using the formula to get the log current and also log scan rate. Scan rate is 1, 2, 3, 4, 5, 6, just log the scan rate. So you got a very straight line. Same things goes to origin, fit linear. Then when you fit linear, you get the value of the gradient, which is the B value. So the B value close to 0.5 signifies diffusion control dominates, while the p-value close to 1 signifies diffusion limiting prominent. So depends on the p-value, you can determine whether your material is diffusion control or your material is diffusion limiting. If you don't like the word diffusion limiting, you always can use capacitive prominent. It's all the same, depends on the application. Okay, next procedure number 9. This is additional data. So you can do this or you can skip this, depends on you. So step 9 is determine the anodic and cathodic R square value. So we want to see the regression at fixed potential, for example 0.35 volt. Find the current response at each scan rate and plot the current versus scan rate power of half. So what happened here? We are finding the current response at oxidation. Anodic is oxidation, and also at reduction. Cathodic is reduction. And we plot current, which is the current response, versus the scan rate power half. And same things using the origin, you go to linear fit, find the R square value. So they have a lot of meanings and indicator what means by the R square value. Normally when we are using ANOVA regression analysis, so we believe that R square value close to 1 is good. In this case, anodic and cathodic R square value close to 1 indicate that the material has reversible capability, which is significant for battery grade material. So if you are studying supercapacitor, it's quite good if you can provide this kind of graph in your paper or your thesis. Okay, that's all I think. Thank you very much for your time. See you again. Bye. I'm Dr. Nur Hafiz. See you again.